Well, I'm starting to think that this week's meeting was postponed and we didn't get the note.
Well, John, I'm not sure what's going on because almost every meeting I've tried to log into in the last 3 or 4 weeks has been either cancelled or postponed. This one was extremely ambiguous. The actual link I got for earlier on, which I put um, into my calendar, was for 10 o'clock, and then I noticed that the one that was sent on the email to the mailing list, I realized that it said 11 o'clock on there. So there was a lot of
Mhm.
ambiguity. So, John, tell me about yourself. What are you working on?
Let me get the video going here.
Let me
So,
let me put
so,
the
so we've spoken a couple times, Paul, um, at the Chiplet Summit, basically, I guess, in one of the pizza dinners. So
okay.
I'm with Crossfire, Chief Product Officer. We're focused on chiplets, have been for a while. And we're bringing to market what we consider a holistic approach to the whole chiplet problem, which includes heterogeneous integration and includes die-to-die interconnect, and it includes just trying to deploy something that when someone other than NVIDIA, AMD, whomever steps up to the plate and actually wants to do something, that there's a path for them to do that. Right now, a lot of these technologies are what I'd call unobtainium. So that's what we're
Unobtainium.
about.
Well, sometimes unobtainium is a failure of imagination on behalf of the designer.
Uh-huh.
Um, and we like to talk about impossibility results and the distributed systems community. And everyone thinks certain things are impossible, and then we have, the basic FLP impossibility result, which basically says you can't distinguish between a node that is slow from one that's failed. Um, and then hundreds of impossibility results came out in the distributed systems literature, and now everyone makes fun of the word impossibility because the word the word that we use to to unpeel this problem and to educate people on a different way of thinking is
Hmm.
circumventing the
Sure.
impossibility. So
Uh-huh.
circumventing the impossibilities, like circumventing the uh, the restricted, inside the box thinking that exists today. So tell me,
Hmm.
which company are you at with? Did you say?
The Crossfire Technologies.
Crossfire. Okay. All right. So how big are you? Are you a small or a big company or a
Oh,
startup or?
we're a very small startup right now. We're under 10 people, but we have, of course, aspirations to be much bigger.
Of course. So where are you on your funding schedule? Have you managed to get some funding to get started?
We are lightly funded at the moment. We're currently doing some fundraising this quarter, and we're starting to ramp that up. We've been honestly spending a while trying to get our story right, because what we're doing, we're just not a company that's bringing a chiplet to market, or that's bringing a die-to-die interface to market. Uh, our CTO looked at the problem a long time and realized that it takes advanced packaging, it takes advanced interconnect technology, and then it takes a business economic based approach to what you do and don't do with chiplets in order to make the industry successful. I mean, I would think this is one of the more important discussions going on in OCP, because it, it it all has to work together. And right now, everything is a very boundary specific and a very customer specific, and really not a lot of off the shelf to anything that's going on in the chiplet world right now.
Hmm. Excellent. So do you plan to be at the Chiplet Summit?
We will be there. Yes. Yeah, we're a
Perfect.
Silicon
And you,
Catalyst portfolio company, so we'll
okay.
probably be uh, in their booth or at their table. and talking to people. We really didn't get ahead of the curve enough to get a presentation submitted and accepted. So kind of
So,
what goes there.
so if you were to get a presentation there, what would be what would it be about? What would be the title, perhaps, and an abstract?
Oh, interesting question. So we would call it the a holistic approach to chiplets,
Okay.
and it would address the three things that I've talked about. Market is encumbered by complex, expensive, and uh, uh, mismatched die-to-die interfaces. We would talk about the lack of chiplet availability for specific vanilla chiplet or system functions like memory controllers, like network interfaces, like storage interfaces that are part of the overall, let's call it table stakes. If you're going to do a system of chiplets, you've got to have these interfaces. But a lot of the times they are, to me, it doesn't make sense to do it for each design that you're going to do and basically buy the same IP, go through the same design process, put it in the same SoC time after time after time for each one of the processors in say you're an XP or an ST micro. Maybe you can do that once and then integrate it in as a chiplet ever afterwards. So that's part of our thinking. And then lastly, we have a heterogeneous integration process that we call OmniDie. Fundamentally, what this is a way to eliminate the silicon interposer from the equation when it comes to heterogeneous integration of chiplets. And all of
Uh,
these
Okay.
work together to we think enable the open chiplet economy, excuse me, to achieve exactly what the industry is hoping that it gets to, and in particular what we at OCP hope that it gets to.
Well, excellent. Interesting. So, I'm putting together the tutorials on the first day of the Chiplet Summit. Um, and one of the things that we'd like to focus on is the chiplet yield. And most of the problems today are it's not just the chiplets need to be yielding off the wafers. It's that when you start to put them together on the motherboard, we're noticing that everyone is running into a lot of interoperability problems. And
Hmm.
so the large companies and their ecosystems, like NVIDIA and AMD and Intel and Broadcom, they all, got the advantage that they've got the resources and they've got
Right.
the knowledge and the IP, which they can start to sell. The the one of the things we're hoping to do is to have bring in the Risk V community because what we realized is that first of all there is a crisis in interconnection. When you first put these
Hmm.
chips together, it's like what the fuck are they doing? It's like
Right.
and
Right.
a lot of it is because of incomplete specifications, uh, incomplete understanding or misunderstandings that accumulate from that. And only when you get them into the lab and you put them on the bench and you apply the power, do you actually see, oh shit, I've got some debugging to do here.
Uh-huh.
So there's multiple levels of this debugging problem. The first one is when you first bring chips up. That's the crisis right now. And what we call this the yield problem, or because that's when you start to see all the incompatibilities of things, and then you have to go back to design and and say, okay, how do we modify the design so that it's actually going to operate? The other part of this is, well, uh, how do you actually put a debug processor um, on that thing that serves as as a BIOS or a baseboard management controller? So
Right.
we call it the chiplet management controller. But
Oh man, that's yes. Yes, 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 yes. We have thought alike on that. Um, yes, please. Didn't mean to interrupt, but that's exciting to hear that someone else is recognizing the necessity for such a beast.
So, one of the challenges with the Chiplet Summit, and probably even more so with FMS and with even the OCP conferences, is everyone is kind of wanting to sell like 3-year-old technology, stuff that is known, 3 years ago.
Hmm.
But usually because they understand that, they've got products, they've got salesmen on the job, they're trying to get funding, they're trying to get customers. And this is a chicken and egg problem. And so we're working with ARM right now, to be on the the interconnect crisis super panel for Chiplet Summit, and
Hmm.
with Tentorrent and with 4 or 5 other companies. So we've got a pretty good panel coming together for this debating that problem. But what
Hmm.
I'd like to do is on the day before, we've got two completely different but closely related um, activities that we're putting the tutorial systems together. And we've got some really excellent people that have volunteered, and then they unfortunately weren't able to come because one of them moved, to the UK and left their house in Oregon. Another
Hmm.
one is in Texas, and he's been sequestered by his boss to go somewhere else to actually do some selling. A third one is working with us closely, but here in Saratoga. And we've got 4 or 5 people who are really, experts in these areas. But I've got agreement on what it is that should be doing in terms of, from from power on to debugging and observing the existing systems.
Hmm.
That's now in the morning. The whole session is going to be about chiplet Ethernet. In other words, what should be Ethernet for the next 50 years?
Hmm.
And the reason for that is because I know Bob Metcalf very well, and the original paper for Ethernet was published in the ACM journals exactly 50 years ago this year, in July. So we're hoping to
Uh-huh.
have a
Wow,
special
has it
issue.
been that long? Holy cow.
Yeah, isn't it amazing? So we're taking this opportunity to say, well, what if you could rethink this whole problem? What if you go back to
Hmm.
first principles, rethink what it is that Ethernet was solving, compare that with what we've learned, in the last 50 years, and say, what would be in the spirit of Ethernet, and perhaps even in the actual letter of Ethernet, could we redefine what Ethernet should look like for the next 50 years? So we're hoping to have a special issue in the ACM, called Ethernet 50 years of learning and
Uh-huh.
then forward outlook. What does it look like? So the whole morning on chiplet Ethernet is really all about what should Ethernet look like for the next 50 years. So would like to kind of like stretch everyone's imagination, get them out of selling what they already have. But what we've learned is that an awful lot of technologists actually know quite a bit beyond the current edge of knowledge, which is, prevalent in the industry with people trying to sell stuff.
Hmm.
And so we're looking for people who can give a tutorial, it would be like half an hour or something like that, on some specific aspect of what would look like, of what this would look like, excuse me, in terms of deep technology. So these are deep technology overviews. They're not, marketing materials.
Hmm.
So I don't know if you might have something interesting you might be able to say on that front.
Not off the shelf. Um, when I so boy, this is a complicated discussion for my brain anyway, because when I think about Ethernet, really it's a network connectivity protocol designed for systems, be they whatever they are, that are geographically far away, quote unquote. And far away is kind of a nebulous term, but that's really what it kind of started out to be. Um,
Now, what we're
and
looking at is there's all sorts of other link protocols that are vying for dominance in the industry. Obviously PCIe has now evolved and become a lot simpler and perhaps more appropriate for chiplet interconnects and into UCIe. So UCIe
Hmm.
is very prominently all over the conference. Intel is pushing very hard to sell UCIe um,
Yeah.
as the next as the chiplet interconnect. But there's all sorts of other chiplet interconnects. UA-Link, for example, from AMD, they're trying to push
Hmm.
that into how do you connect GPUs together side
Right.
by side.
Yeah.
Um,
That's
and they
kind of an
realize,
alternative to NVLink, more or less, right?
well, and then there's yeah, it's well, they're trying to make it an alternative, but I don't see it as being good enough to actually replace NVLink. NVLink
Hmm.
is seriously far ahead in terms of their
Yeah.
experience, reliability, their sales,
Hmm.
their market domination, and so on. So I have a paper in development working with some of our team that says that UA Link is not great. And it's
Hmm.
intended to be a gentle critique of where their thinking is still, deep in the past and how you might be able to reconsider what that might be able, what that might look like.
Hmm.
Um, and I also know the folks at NVIDIA pretty well. I brought Michael Kagan, the CTO of NVIDIA into the FMS conference for the CTO Vision panel, and we
Hmm.
had a very lively, extremely good panel on in FMS. Um, and so the challenge here is if you really want to do something and be noticed, you have to be to NVLink, not just by some percentage. It has to be 10x
Hmm.
better. And
Yes.
everyone is battling now on trying to get their technology to give the fastest links, and it's 400 gigabits is deployed today, 800 gigabits is going to be deployed this year
Hmm.
sometime, 1.6 terabits, and these are all per lane, by the way, and it applies to all of these things. It applies to UA link, it applies to UCIe, it applies to NVLink, and it applies to several other. When you're communicating from one chip to the next in a sea of XPUs, you end up
Hmm.
with a very different philosophy on how the communication fabric should work.
I
So,
can't argue with that a bit. So we look um, at the chiplet space in two broad categories. One is what I'd call beyond the reticle, and then the other one is within the reticle or between the reticle. So in other words, you look at what's going on mostly in the AI space, and we're taking die that are three-quarter reticle size or larger and turning them into what NVIDIA calls a super chip. Right. Now, I call it a super SIP because in reality, it's a system and package. Um, but
did you say super cell or super sock
it's called a super chip.
or super chip? Okay.
Yeah, yeah, that's what NVIDIA calls it. In reality, it's a system in package or system in advanced package, if you want to call it that. And to a certain
Okay.
extent, the interposer has become the baseboard.
Okay.
Right? And then you have um, an entirely different set of use cases where you're looking at SoC disaggregation, where maybe you're looking at putting together a processor that's going to be 8 by 8 or 10 by 10, but you want to, for various reasons, for economic reasons, for market product management reasons, so you want to do a fill all niches strategy with your product line, and you have a base processor that you round out with different peripherals, etc. That's also another good use case for chiplets for heterogeneous integration. The problem that I see in the industry right now is that everything is really targeted toward beyond the reticle,
Okay.
where you and really what we're trying to fix is to simplify things and make, okay, let's say we want to build a 20 by 20 chip and we want to do it so that we harvest the supposed theoretical advantages of chiplets, which is lower cost, simpler design, etc. But then you look at, okay, how much bigger does your overall silicon consumption become if you start trying to stitch everything together with UCIe? And how complicated does your system design become when now you're trying to run 64 gig links, taking a look at the latest UCIe standard, multiple of those in between, let's say we turn this 20 by 20 into four 10 by 10s. Um,
So when you say a link, are you referring to one lane or multiple lanes?
well, I'm referring to a die-to-die interface. And so I'm not sure what the smallest component or a version of UCIe is. I think it's a by 8, but I could be wrong on that. Uh, but trying to put that down along the edges of your die takes that 10 to 10 and blows it out to about a 12 by 12. So
Okay.
now you're really not achieving what you were trying to achieve. Ideally, you want to interconnect those chiplets at the same interconnect density off die that you do on die. Someone at TSMC called that the interconnect pitch gap, which is the wire pitch between difference between on-chip and off-chip interconnect. And really, every time you see a SerDes, when you boils down to what the problem they're trying to solve is there's no way to get enough wires between point A and point B, so you have to shove them into a pipe.
Okay.
Well, does that resonate? Kind of
Makes,
make sense with?
it makes a lot of sense, yes. I'm just checking, see if you're in my contacts here. So I don't have you in my contacts. Can you do me a favor and put your email address in the chat?
Absolutely, absolutely. Let me find the chat window here. Here we go. And so what we're all about is wire abundance.
Okay. I'm wondering if I mean, would you like to give kind of like an advanced technology tutorial at Chiplet Summit that you could call it, you could actually say, beyond the reticle, or between the reticle.
Hmm.
That could be maybe a title of the talk.
Hmm.
But then what you're describing here, your wire abundance, I presume that you're already thinking about a bunch of wires, and forwarding clocks and that kind of thing.
We very much are thinking about source synchronous interfaces. Um,
Okay.
and one of the things, but even the source synchronous interfaces look a lot like SerDes because now you're starting to see Reed-Solomon, forward error correction, that kind of thing in some of these interfaces. Uh, and to me, that adds latency. And eventually, what Ethernet, what storage, what any of these interfaces are eventually all about, it's about getting to memory. And the slower you make that process, the less utilization you get of all that expensive hardware that we've bought from TSMC because 40,000 processors are sitting there waiting for data to come back to them. And we do
Yeah.
all kinds of manipulation in the coding and the data structures and trying to make this efficient. But ideally, what you want is you want terabytes of data, tens of terabytes of data going straight to memory in these systems.
So
So,
yeah. I
and
used to
so,
design memory buses, cache coherency stuff at Sun Microsystems, by the way. So my background is deep in the hardware, but these days I'm the CEO of a software company trying to build on top of this.
yeah, we never forget our hardware roots, though, right? I started out doing hardware design and fiber optic transmission systems, and then got recruited in LSI Logic, became an FAE, um, got an MBA, went over the dark side, started doing product management, strategic planning, all that kind of stuff. But the the good thing about that was being an engineer, I could tell when something was technically challenging versus when the engineers just didn't want to do it because they wanted to work on something else. And
So yeah, I have discovered that a lot of engineers can't tell the difference between what can't be done and what they can't do.
right. And that is very, very true. Especially, I mean, sometimes you don't need to develop it in-house. You need to go out and find someone that's already done it. And that never is a easy sell. But anyway, that's a little bunny trail. I'm sorry, I'm going to stay
No
on it.
problem.
But the point is that yeah, eventually all these virtualized software systems have to find some transistors to do the work, and that's the hardware. Um,
Absolutely.
yeah.
So who is your CTO?
His name is Kevin Atkinson. He's also our CEO. Um, Kevin, how it's an interesting story how he got into this space and how he started the company. He built probably what I think we both agree is the first serious tensor processor in TSMC 130 micron silicon. It had 400 1 gigahertz um, processors, and this was for a company called MathStar. And the idea was would compile math into these processors. Um, the problem he ran into right away was that they had multiple DDR2 interfaces, which was what was the standard at the time, and all the processors were sitting around waiting for work to do. It was you just couldn't feed the beast, and so that problem. He said, this needs to be solved, and the problem's only gotten worse because now you've got these chips with over 20,000 cores running at well over a gig that are trying to be fed, and DDR has only gone from DDR2 to DDR4 or 5 now, excuse me. And then you've got HBM2, but even so, even with all that bandwidth, it's nowhere near enough. But we've done just some rough back of the envelope calculations, and you really need 50x bandwidth kind of in a flat memory space. And that's really the big problem is getting a memory space flat enough that as the models get bigger, you can um, all the different processing units can um, access the data relatively quickly. So latency is key to us. We think we solve it with what we call our direct chiplet interface. Um, that name has stuck for quite a bit. While I'm let me finish up this um, email.
Okay, sure. I'm going to go
Or
and check
yeah.
my breakfast. I've got some oats cooking, so let me just check it's
Okay,
not
sure.
cooking over, boiling over. Oh, I'm doing just fine. I'm on an 18/6 fast, so I have all my calories between noon uh, and 6 p.m. and it's
I I need to do something. I'm heavier than I've ever been, and it just seems to be tough to find time to go work out. And it's but yeah. Anyway, so I've heard of that. I may have to take a look at it. And how's it working for
it's
you?
working wonderfully. My health is better than it's ever been. And my ADHD is kind of like much easier to manage. It's down to a dull raw. And my mind is clearer. productivity is higher.
Hmm.
So yeah, I'm doing very well with that. So it's basically I don't eat between, 6 p.m. in the evening and noon the following day. And I have breakfast the things, around about noon. And then I
Uh-huh.
have like dinner at 5:30.
Hmm.
And
And that's it.
it's
Wow.
working fantastically for me. I'm surprised at all the health benefits.
Yeah.
It's I'm healthier than I've ever been. I don't have a single thing wrong with me.
Yeah. Well, you had me sold on ADHD because that's that's one of the things that my kids say I battle a lot. I argue with them, but I don't know. They may be onto something. So, um, so first of all, thank you for the opportunity to share my thoughts. I'm inclined to. I mean, I would like it to be useful and not just you know a marketing pitch, but this is how we truly see the industry and we truly see what the industry needs, right? Is a way to deal with inside the reticle and how you really ma achieve the promise of chiplets. Um, so I'd be delighted to try and put something together for you.
All right. Well, I'm not going to promise anything. But it's possible we can actually do that. But it needs to be forward looking. Um,
Hmm.
one of the themes that the organizers are actually interested in is data centers in space, data centers on the moon, data centers on Mars. How do
Hmm.
we tackle that problem? Because that's not so far off. What it does is it puts the uh, the context of what it is that's being developed from what people already know how to do but haven't yet done it. Maybe
Hmm.
don't know this is, and as you mentioned, power dissipation, saving chips, bandwidth. These are all things. The 50x bandwidth that you're describing here is just a function of how many wires do you have times what is the lane rate. But
Hmm.
it's actually more than that. When you look at the physical bandwidth, people like to count all the bits to put into packets and, multiply that by the bit rate and say, oh, there's my bandwidth. And they try to sell that with those SerDes. Everyone does that, including NVIDIA or Mellanox, who I
Hmm.
used to, and AMD and Broadcom. But I'm thinking it might be the wrong way of looking at things because if you're pushing all this bandwidth through the system and some of it is speculative, it never actually works, it doesn't get there, then that speculation is just wasting energy and not giving you any benefit. And it has this terrible problem that when some of these packets fail to get through, the only choice that the higher level applications have, including the AI ML, training
Hmm.
systems, is timeout and retry. And we've
Right.
long known in the distributed systems community that timeout and retry is the root of all evil. And so
Pretty much.
instead, and we have built in the OCP something called the atomic open atomic Ethernet.
Yes.
The spec 0.7 is out there right now. I can point you to it. But the whole idea is to eliminate timeout and retry because it's such an unnecessary, wasteful thing. Um, we are very familiar with the meltdowns that happen in large data centers. When I was at Apple,
Hmm.
we used to see them happen about once a week, and where all the machines would get locked up. And sometimes the only solution would be to reboot them. I mean, we have some
Right.
band-aids, like we would take Zookeeper, for example, and we would just automatically reboot Zookeeper like every 5 minutes. Fuck it, it's just like use a
Yeah.
hammer.
Uh-huh.
And
Uh-huh.
that what
Sometimes
would
you
that
have to.
do is what that would do is because Zookeeper's kind of like Paxos, but not really. It's not good enough in terms of a protocol. So everyone's trying to move away from Zookeeper, at least for the last 10 years I know of.
Hmm.
But then, what else the alternative? People using uh, other versions of Paxos and Raft as the consensus protocols to try and bring them together. So we're seeing the problem at that layer, and we're looking right down into, well, what's causing this problem? And we think that the problem is caused by not having interaction at the links. In other words, the
Hmm.
protocol, instead of cramming as much bandwidth as you can down the link, and then getting, using credit-based flow control or whatever else, and then trying to get, some kind of like, feedback model, control theory model of congestion, for
Hmm.
example, so that that doesn't happen. Well, it does happen. It happens everywhere. And the closer you get to the edge, the worse it is. So we see entire, you know, floors of data centers go into this meltdown stage where you have to kind of typically it's on an application by application basis, but it happens so much in microservices with at Amazon, for example,
Hmm.
and Microsoft Azure, in Alibaba, and in Google. And so one of the things that's happened very recently, which is related to this, is like, let's take another look at bandwidth. Let's go back to first principles and say, what, people for years have talked about, throughput versus good put, which is, the throughput is like, you're trying to cram down the wire. Um, what we call imposition networking. You impose on the network and the endpoints, here's what I want to send you, and you force it, and you use TCP/IP to kind of like do a back off or whatever else. And
Hmm.
that's all what the way the internet works. But at
Yep.
layer two, we could do things that you can't do over the internet. At layer two, you can actually redefine what bridges are. You can redefine what learning it is. You can, and
Hmm.
you instead of having broadcast protocols that try to search the layer two topology space and say, okay, keep on broadcasting this until it doesn't work anymore. And we've discovered that doesn't work. I mean, 10, 20 years ago. Trill,
Hmm.
was the big thing. Everyone said, fuck it. And they all went to layer three to do their routing and said,
Hmm.
that's got the mechanisms in it to actually try to keep this meltdown problem to a dull raw. So redefining bandwidth is like from first principles is a really interesting problem. Um, it's not just good put. It's like um, if you want memory interactions, you better have really, really short fucking packets. Like, and so if you've got
Yep.
source destination addresses in there, if you've got all sorts of, 50-year-old paraphernalia that the IEEE 802 committee have dropped in there and never and forgot to take out, then
Hmm.
all of these extra bits, just make the packets longer. And so one definition of bandwidth might be inverse latency.
Sure.
Okay, and then that says, well, okay, this is now why we understand the high frequency trading industry is so hell bent on lowest possible, ultra low latency. And
Hmm.
they've got all sorts of tricks and treats for being able to do that.
Yep.
But going back to first principles says, well, hang on a minute, we can use exactly those techniques, between, a chiplet and its local memory. HBM, these different levels of DDR2 to DDR5 or HBM2, they're just bit rates. It's like, well, if you
Hmm.
go back to the first problem, is like, well, what's the point of stuffing bits down the wire as fast as you can if, every 48 seconds, the link is flapping. And that's what
Hmm.
that's the number one problem Google's having, that their MTBFs um, of the actual failure on the fiber and the lasers
Hmm.
and the connections and everything else. Those are happening, every 30 or 40 minutes in Google
Right.
sized infrastructures. This is, with a, 10 to 100,000, nodes, and a million links somewhere. We won't
Hmm.
count those just yet. But what they're finding is that their MTBFs of to failure of the links. And when I mean a real failure, when we have to send an engineer in to go and change the fucking connector, or clean the optics, or
Yeah.
tune something. All of that's one thing. But what they discovered is the number one problem at Google now is link flapping. And what's happening is those links are going out of sync, and the servers are having to like resynchronize and restart
Hmm.
every 48 seconds.
Oh my gosh.
Oh
How long
my
does it
gosh,
take to
yes.
restart?
Well, sometimes minutes for those links to restart. I mean, at least, many seconds, 10 to 20 to 30 seconds before all of the routing tables have reconverged in the switches. And
Hmm.
that that we think is a really good reason to go back to first principles and say, what's going on here? Um, do we just spend more time and effort designing, more and more reliable links? Trying to get the tolerances right on everything, trying to get the
Mhm.
interoperability to work properly, trying to get the phase locks loops on both sides to kind of like, jive together and get into sync with each other. Um, and then, as you pointed out a moment ago, I think adding, more bits, forward error correction, having
Yeah,
codes and that kind of thing, and EDC of all kinds. That's a narrow box that everyone's thinking in.
yeah. But wouldn't you say, or we could hypothesize that these problems were being solved at the wrong place in the stack?
Yeah.
This isn't necessarily a TCP/IP job because that protocol was written for a different world, and it's maybe not even an IP job. I mean,
Yeah.
where do we do this? And I think where you're at is that it needs to be down there at layer two or maybe even layer one,
Um, yeah. Let me just I just want to save your
because the higher up the stack you go, the longer it takes to figure out something's wrong, and the longer it takes to recover from it.
um so you're getting the point here. You're really getting the point. Fryer is Fryar. Okay.
Yes,
I'm just putting it into my notes so that when the Zoom goes away, I've still got a copy of
yes.
your email
Isn't that
address.
annoying?
Yeah, it is. I'm planning on talking to the organizers of OCP to see if we can find a solution to that so that Zoom actually, it's not that everyone should be forced to save the chat. The chat should be saved automatically in the record
Hmm.
that could be on the
Yes.
wiki things. So I'm going to point you to a web page here, which has a lot of these problem statements and the solutions, which is the Open Atomic Ethernet. It's in the link. In fact, I can bring it up on the screen if you'd like me to share.
Yeah. Is this in the same application area as Ultra Ethernet or
Well, Ultra Ethernet does exactly the wrong thing. What we've discovered is that Ultra Ethernet is trying to spray packets across many links in order to, because the only thing that Broadcom has to sell is bandwidth. Um, and
right?
and that's the wrong paradigm. It's like you don't need to go through a switch. If you go through a
Well,
switch in a sea of chiplet, is a sea of XPUs, let's call them. Um,
but
then you're going to find that the switch latency itself is making the packets, the
hmm
end the latency much worse. So the real
yes, which is the opposite of what you want. I mean, that's just link aggregation
yeah,
problems you're bringing dragging along. Hmm.
yeah, it is, and all of the multiplexing problems. I mean, there was a great paper by a networking expert from VMware that was called I don't know, something like multiplexing is evil or um, yeah, multiplexing considered harmful. I think it was. It was a good. It's a takeoff
Yeah.
on the, you know, premature optimization is, the root of all evil. Um, but
Hmm.
the so this is Open Atomic Ethernet. Um, I'm going to actually what I will do is let me bring up the slide presentation because I can show you some of
Sure.
the things that are going on here.
Yeah, this has been on my radar. There's just so much right now. And we're kind of inside the package is where we're
Yeah.
starting our focus.
All right. So I gave this presentation at the OCP TAP meeting, um, and I've also given a similar one in some of the Open Chiplet meetings to
Hmm.
describe what's going on here. Um, So the problem that we're solving is from a distributed systems perspective. And the issue here is the MTBF of LLM training at scale. And so there's a lot of work here in this Alibaba paper, which really has that pie chart on the right-hand side here
Hmm.
about all the reasons why the training fails. And this is why you've
Hmm.
got so many different you know processors that are all sat there waiting for something to do. Um, the second one here is all about database bottlenecks. The link is here. I can send you this presentation after the slide, after the
Sure.
meeting. I've got your email. Database semantics, database corruption. This is where all of the corruption of data structures are happening. And the problem is all of these are silent. Um,
Hmm.
when you compare with what's going on here, we find that topology management is a big issue for NVLink. The academics have tried writing papers on NVIDIA's uh, NCCL. Let me put this into presentation mode, and then you can see the whole slide. And so this NCCL thing is the communication strategies. And so they're looking at once you've got the links up and running, what is it that you're doing in terms of trying to make communications happen? And this is between two NICs,
Hmm.
obviously the NV link here, host memory. I think that's a bad idea. The host memory isn't really there. It's up above the PCIe bus. Um, and this method of what they're doing at the same time is there's a bunch of papers from Stanford folks and Nick McEwen's team there on Nano PU, which is about how to make all of this much more efficient by doing instead of calling it a memory to memory interface. By the way, memory to memory or shared memory systems,
Hmm.
every architect on the planet I know of has bent their pick on that problem for the last plus decades, 3 decades. Um, and no one has actually been able to get it working properly in practice. And the reason for it is it turns out that ultimately you can't do it with reads and writes. Reads and writes always leave a gap in between them where you can't guarantee that things can be atomic. So that's what the Open Atomic Ethernet Protocol aims to solve. We don't use reads and writes, we use swaps. And it turns out that then gives you a direct connection into how you can deal with ownership and borrowing inside the memory on both sides. So we do it only register to register. So we're trying to do this with RISC-V processors right now, extending the
Hmm.
register files to literally the memory connection between the systems. Anyway, I'll go to the point. Here's the
Yeah,
main
yeah,
slide.
yeah. I get that. That's cool. Hmm.
So it turns out this simple discovery that you can't do distributed shared memory with reads and writes. And yet everything, CXL included, is all reads and writes. It's
Hmm.
like, haven't you guys figured out yet that that doesn't work? And and it's amazing that the whole industry can lead each other, down the garden path and into a quagmire of complexity that they can't get out of. So this is the data from Google. So Google's basically saying that they're getting optical failures, every 30 minutes this year or last year, and that they're getting
Hmm.
optical link flap. The mean time to flap, they mean here. That's the mean time between failure and mean time to flap is
Hmm.
48 seconds. So what's going on here? That the Open Atomic Ethernet is the Ethernet for the next 50 years. And we're also doing several presentations in the morning tutorials for Chiplet Summit, going through all of these first principles analysis, showing some new results. There is some mathematical results. There are lots of simulation results. And we also have formal models described in Promenade and Spin and in Mathematica and other tools to actually show
Hmm.
how this problem happens. So the problem is failure detectors. Um, you can't tell whether a link is failed or not. Um, what we're good doing is popping up a level. Let's imagine we wanted to go into space. Elon Musk and several other organizations, I think including
Hmm.
Amazon, now say they're going to put data centers in space. Because they can get lots of free sunlight, they can deploy very cheap uh, arrays of photosensors that can turn it into electricity, and
Hmm.
they can, batteries there, to put them over but now that the batteries are all lithium, so they're much lighter. So what would you do if you wanted to put in data centers in space or data centers on the moon or data centers on Mars? Well, the last thing you would do is ship an army of system administrators with it to fix it when it fails every day, or every or when it fails, or algorithms
Several times a day.
yeah, several times a day. So what the goal here is zero administration. So we replace humans with graph algorithms, allowing everything to be self-configuring, self-healing, and self-organizing. So that's the high-level goal. Um, we do it by basically taking the links, and this is an example of a SODES with back-to-back Shannon channels. So in other words, instead of just throwing the data over the wire and hoping it gets there, and then having to work in this very narrow band of bit rates that everyone has to test their compatibility with plug FETs and so on. We're saying no. There's a much better way to think about the nature of time, the nature of synchronization here, and it has to be bidirectional. And what you're looking at here is the center of the SERDES in gray is basically the first 64 bits of the first slice. The one in red is the next 64-bit slice, so it's the second slice. The orange one is two slices, so that takes you a total of four slices I've got up to now. And then the yellow
Mhm.
one is eight slices. So there you go, a full Ethernet frame where we've redefined how the encoding works so that you've got um, uh, you can actually go out and manage topologies at layer two brilliantly. All of this is designed, it's all been tested, it's all been working for a while. It's still evolving, and we're at version 7A on the spec right now. So this is how it works, and this is what I wanted to talk to you about. This thing on this is the connection between the chips. Now, it turns out you can do all of this in parallel with back-to-back clocks in
Mhm.
an interesting way. Um, and just going right back to how what are the ways that you can synchronize things over a parallel bus or serial bus. And it turns out that everyone gets sucked down the path of building trees of clocks so that you can forward the clock on each of the things. But
Mhm.
then when you've got something coming back from memory, you have to kind of like schedule that because the communication is much faster than the cycle time of the DRAM or even SRAM. Um,
Mhm.
and so all of this is really easy to fold up or down into parallel interfaces or into serial interfaces, as you can see here. But they're all
Mhm.
based on the same principle, back-to-back Shannon channels. Now imagine that one of these, you see those oval loops, those links between the nodes? So
Mhm.
imagine what you're looking at here is essentially a chain of links that's going through a system of some kind. And what we've discovered is that you cannot solve this problem this way. It turns out that in order to get the complementary information state on both ends, you'll notice that the green and red and the red and green on the other end are complementary. We call this entanglement as opposed to quantum entanglement because we're actually using
Mhm.
classical methods to use something called the no cloning theorem, which you can do classically to guarantee that if all these links are working, we can guarantee that both ends of this link are absolutely in sync with each other. It's almost like a TikTok. But you can push full bandwidth down each of these links. But when something breaks, you could have to solve it with a triangle network. So these
Mhm.
atomic link, all these atomic links, they're all atomic links. Everything's atomic in this, and this is fully defined in the spec. So when something fails, you have to use triangles to provide error detection and recovery. The remarkable thing is when you're using this perfect information feedback on each individual link, you can mathematically compose this over any number of links, over arbitrary chains or DAGs or trees. That's what we've discovered we can do at layer two without ever having to go to layer three or
Mhm.
above to IP and TCP IP. So there you go. That's basically how it works. Any questions?
I understand the concept. I have a lot of work to do to figure out exactly how it's all working under the hood, but yeah, fundamentally, just to simplify it, we push the work down into the link layer instead of IP and TCP/IP. Is that fair?
Yes, well, it's you say all the work, but the thing that we've discovered is that we can dramatically simplify everything. So all that work turns out to be very simple distilled protocols that do nothing but guarantee this Shannon slot reconciliation on both sides of the link. And so
Hmm.
we've discovered how to dramatically lower the latency. We don't need any, because all of these links are defined by higher level trees. It turns out that the protocols don't need source and destination addresses. They don't need error detection. You can eliminate FEC because
Hmm.
what we've got is a back-to-back protocol that guarantees that the information was passed. The tokens are passed from one side to the other. I want his. This is how the actual bits and bytes works. Um, Notice that I've got a 40, a 68 slices, 60,
Hmm.
64 byte frame. What we do is we have these different styles of mathematically they're defined as operator and operand. You
Hmm.
could call it a payload, but the operator and operand are basically the alternating bit protocol. So it's something that no one can patent. Um, but we've discovered how to utilize that to build something that is far better than anything NVIDIA can do with NVLink. And not only that, we can put in the link. You talked about all of your CTO's um, machines that are sat there waiting, needing more
Hmm.
bandwidth, waiting for work to do. It turns out that we put a linear algebra engine in the link itself. It's just multiply and add. And it turns
Hmm.
out that multiply and add is really a simple, Hadamard set where you're using plus or minus one and also plus or minus zero in the information. It's all mathematically consistent with Shannon's theory, but it's back to back. It's two-way instead of one-way. So there you go, with the bits on the wire and the bits in the memory all the same. So the link is a linear algebra engine. It computes 2, 4, and 8-bit weights from atomic multiply and add. And it does it faster than you can do it in any GPU or any XPU or any
Hmm.
IPU. Intel's infrastructure processing unit is actually one of the models that we're trying to work with. So any questions here?
No, not right now. That's obviously a few
See where we're
gates,
headed.
but
It's yes, but it turns out that all the gates are very small. It's a really
yeah,
short logic
super
path.
small. Yeah.
It's really small, and so it turns out it doesn't. We can do it. Or we've tested all of this in FPGAs, and we know that it works. And all of the theory of limited this minimum or economy of mechanism is where
Hmm.
you've really revolutionized Ethernet to really get rid of all of the ornaments on the Christmas tree that's been built up over 50 years and eliminated
Hmm.
everything except the absolute minimum that needs to be on the link.
Hmm. Yeah.
So this is how
So,
we go
can
ahead.
I ask you a question? So,
Yeah, sure.
what if you didn't need the SerDes? What if we could give you the same bandwidth or the same throughput, good put, whatever you want to call it, between chiplets with just adding wires until you have what you need? And like we have a roadmap up to 10,000 wires per millimeter of beachfront.
Okay, I'm going to write that down. That sounds like a nice lot of wires.
Yeah, and that's the roadmap. Right now, what we're working on is taping out a proof of concept that has and this is um, we fit all this in the seal ring of the IC, so it's not like you're going into the uh, into the logic area of the chip. So we're about, let's call it 100 microns deep into the chip, just to be conservative. And from there, we're going to start out with 1,000 wires per millimeter just on our proof of concept. with so what's that, 50 square microns, and then we're building up from there. And a lot of that is limited. We basically get down to the limitations of lithography as far as how uh, dense we can put our wires.
Let me just turn off my oaths for a second. I don't want it.
Certainly.
Okay, they're all good. Because of my ADHD, I have a tendency to burn things. All right,
I have done that, and yeah. So
all
fundamentally,
right, so
that's our
let me go further. Let me show you a few more slides because that's
okay.
just the way that the link layer works. So what I'm going to do is I'm going to show you, we build the system up from the ground. We use puffs for actually doing the cryptographic identities, but we give a cryptographic identity both to the devices as well as to the link itself. So let me take you
Okay.
to where this is going. So what you're seeing here is our physical model. Sorry, not our physical model, our logical model. So what you're looking at here is the exact thing that you're talking about here. Um, this is a logical, not a physical interconnect topology. So we by being able to control the link and which direction it's going and what it's
Hmm.
programmed to do that day or that hour or that minute. We can actually take this sea of XPUs, and it turns out that you cannot solve um, the vast majority of failures with a Cartesian coordinate system. And so I'll show you what. So what we're doing here is we're taking this, and if you look at the actual connections, the beachfront here obviously isn't 1,000, wires per millimeter, but the principle is identical. You can put, eight, channels here, or 800 channels here, or
Hmm.
8,000 channels here. It doesn't make any difference. The model is exactly the same. So the beachfront is not just a a side-to-side thing. This is why these octagons are a logical diagram and not a physical diagram, because you've got the ability to do an octavalent network. So that whole thing
Hmm.
is an octavalent network. So let me go beyond that. So this is what we're able to control. This comes from a bunch of wires specification.
Yeah.
Um,
Yeah. I recognize it.
and we actually don't really want to do the fixed size because we think that's an unnecessary waste of redundancy. So
Hmm.
if you've got data centers on the moon or in Mars, the last thing you want to do is not have some functionality. So we could give you absolute maximum functionality with either static bidirectional, dynamic bidirectional, or simultaneous bidirectional. So all of this must be familiar to you, but you can do
Hmm.
this at 1,000 or 10,000 per millimeter. Now, what the problem we solve as a software infrastructure company is we solve the bring up problem. So each of these XPUs they come up um, as sending a message on these links. And you can have as many of these links as you want. There's
Hmm.
five speech front. That happens to be the limit of my OmniGraffle package that can connect things, easily from one thing to the other. But the principle is
Uh-huh.
identical. What we do is we take the whole of this 3 by 3 sets of tiles. It turns out that the 3 by 3 is the optimum topology in order to give you maximum resilience and redundancy. And so if that XPU in the center fails, then all of the deputies around the edge of it can all take over and continue to do what they were doing so that you don't have to take the whole system down. Um, Now, let's go from the beginning here. So I'm starting here with a substrate of links. There has to be two directions here in our model, only because we're compatible then with the way that Ethernet works both directions. And it's true for HBM as well. You have to have, a path to back, but what we can do
Hmm.
is we can add this software control over all of these links. This is what our companies does. So this physical interconnect is based on a bunch of wires, and it allows us to solve this problem. Let me get this thing out of the way. So what we're going to do is we're going to put a polar coordinate system on this. And so let me put this up here. And instead of using a Cartesian coordinate system, which always has to have an origin, and that origin is always
Hmm.
fucked up, and you really can't solve, most of the problems. So we're going to put a Cartesian coordinate system on here. Think of this as like the 8 points of the compass. It turns out to map directly into the way that you can build modules and motherboards and that kind of thing. Quite simply, we call it, it's not too deep, it's not completely planar in a mathematical sense. It's pseudo-planar because you have got some crossing wires, but motherboards and PCBs these days all have multiple layers.
Oh
So
yeah.
even if you microstrips and strip lines, you've got the idea of what's going on. So this bunch, we're turning this into a bunch of channels. So the letters mean here is due north and northeast, due east, southeast, due south, and southwest and due west, and so
Hmm.
on. So when we come up, we can talk to our neighbor, and we know what we're connected to. You could be connected to anything and not know. So the first negotiation is every link has to be a pair of connections. The fixed directional is not recommended, so the static bidirectional. So every link is at least one pair of conductors. The 3D logical connection topology basically means that we have to, solve I told you earlier on in a previous slide that we're solving this um, failure problem using triangles. You have to
Hmm.
have triangles. It turns out, so we do the allocation of who's Bob, who's Alice, and who's Carol, in order to be able to reliably fail over. So let me show you the interesting part of this that you might kind of like. So this is an octavalent interconnect topology, and every one of those black links has to be at least two. It can be 1,000 or 10,000. Every one of those black links that you see.
Hmm.
But what we do is when we bring the system up from software, we can have this compass point topology anywhere we want. Um, but we can switch them around. We can actually just have them twisted, and so we can have
Hmm.
any orientation you want. So all of the chiplets can come together with this. You might call it a polar coordinate system. Once you go to a polar coordinate system, you can fix any failure in the system by rerouting. So this is where I think this fits with what you're doing. What else do I have? Anything interesting in here? Oh, that one still spins. So what we've got is a whole bunch of protocols that we've built and simulated and implemented. This is what we do is we send out scouting protocols instead of routing in this octavalent mesh. And
Hmm.
when you compare this to a clone network and you look at the congestion that happens, you can see that all the congestion occurs in the switches.
Hmm.
Yeah, and this is actually, we can model this any way we wish. We've got very extensive mathematical models that actually shows how this thing works. So what we've done is we've basically proven that switches and routers are barking up the wrong tree. You need to have um, chiplet fabric communication that can go over any link, and not just like this one does, and not just never mind. I'm going to go past this. All right, here's another
Hmm.
example. We call it the algorithms are called AND algorithms and B algorithms. These aren't new. I mean, the complex adaptive systems community at the Santa Fe Institute invented all of this shit like 20 years ago.
Hmm.
And so what we've done is we've just put it into code and we've said, what does it look like and how does it behave? Can we break it? Okay. And you'll notice that what you've got here is a deteriorating system. Let's say it's on the moon or it's on Mars, but
Hmm.
loads are missing, links are missing, and what we can do is we can still route on any available link by using these the local observer view algorithms instead of
Hmm.
what's God's eye view algorithms and existing networks. So
Mhm.
anyway, that's what we have.
That's cool.
Um, so I'd like to go back to this slide because, well, first of all, that's the topological model that we do. We thought it was about time that topology was brought in into the chiplet community. The problem that we're solving, I'll remind you here, it also includes topology management, which is the biggest problem that NVIDIA has right now, and the academics are having trying to manage the topology construction. We can
Hmm.
do that very well, but what we're going to do is we need to take every one of these links. Here's an individual link. Here's a string of them in an
Hmm.
arbitrary chain. We can take this diagram and we can make it vertical so that all of these connections are in parallel instead of in series.
Hmm.
It's exactly the same software model, the same navigation, the same algorithms for failover. And we can also manage if you've got like, 8 or 16 lanes connecting Ethernet from one chip to the other, we can reprogram those lanes to do anything we fucking want. Because of this model. It's basically graph theory on steroids.
Oh. So, unfortunately, I have a call coming up in about 10 minutes. Um,
And that's fine. And I'm hungry.
so let's
But I
talk
want
about next steps, I guess. I'd
yes,
like to have you run through this if you can find the time. This this presentation with Kevin, our
okay.
CEO, CTO. Um, he will understand some of the higher level mathematical concepts better than myself. Um, and we can figure out um, whether our DCI is fits into, and I guess actually I'd like to make sure it does fit into what you're doing it as a replacement for a SerDes or a UCIe PHY or whatever the case may be. Um, I
Well, we
like.
use we use standard files, everybody's standard systems. We don't change any of that if we don't have to.
Hmm.
Um, and while we can use that, we can also improve the files quite significantly by eliminating FEC so that the packets are shorter and the latency is a lot shorter.
Hmm.
But the model that you have basically is the parallel extension of what we're doing. I actually do have in another slide presentation, which I'll show you and Kevin when we schedule that meeting. I actually have one that shows all the parallel connections as well.
Hmm.
For example, for HBM.
That would be very interesting to see that. Oh, okay.
All right. Well,
All right. So I guess there's that. And do you have do we just need to swap times that would work, or how do you want to do that as far as getting the next meeting?
I'm going to send you an email right now so we're connected. So let me go to the chat and pull up your email address again. Um, this damn Zoom workplace doesn't let me go into my email system. It keeps putting me into the Zoom email.
Oh, Paul, I may have your card
Okay,
somewhere.
here.
But just in case, let me just jot it down.
Okay, I'll just send you an email just now. Look in your email
Oh,
to
okay.
see if you've got it. And the title is just connecting.
Yep, got it.
All right, so why don't you propose a time? I don't use Microsoft Teams.
Okay.
It's too
We
much
have a
problem.
Zoom
So
account.
you have a Zoom account. That's great. I would actually, if I use my Zoom account, I can use my transcript and I can give you a copy of the transcript as well.
Perfect.
If I record the meetings, it's just between us. If there's anything private discussed, it will not be go to anyone else. That's my deal with everyone when I use my Zoom account. So let me go and get some breakfast and then I'll send you a actually why don't you reply on that email and just tell me what times would be available for you and Kevin?
I will do that. I will.
I'm
I'll be
I'm
talking with him
available
later on this afternoon, and we'll nail that out. I'd like to do it tomorrow or Friday if that works with you.
tomorrow. Tomorrow works great. I think tomorrow afternoon works great. After
Okay,
2 p.m. I've
after
got
2 p.m.
meetings. Yeah, I've got meetings all morning. Um, Friday is not bad. I've got two, three meetings on Friday, and oh, actually, I'm meeting with someone from Intel on Friday afternoon. So tomorrow afternoon would be fantastic.
Okay,
After
so after
2 p.m.
2 o'clock, and you're Pacific time, I'm assuming.
I'm in Saratoga, so yeah, I'm Pacific time. Where are
Okay,
you?
I'm in the Raleigh-Durham area, uh,
Oh, okay.
Carolina.
So
Kevin is
I've
in Minneapolis. I'm,
well,
I'm
look, I'm
used to
used to
doing
all of
late
these different
calls.
time zones. Okay. All right, John, it's great talking to you. You tell
Yeah,
me
Paul,
what
you as
time
well.
you and Kevin can make it,
I'll,
and
I'll get
what
that to
time you
you
can
by the end of the day
make it.
here.
Thank you.
Yeah, thank you too.
Have a great
Take care
rest
now.
of the
Look
day.
forward to the next
Okay,
meeting.
bye.
Okay,
Bye.
bye-bye.